Good morning. This content covers the important theorems on linear transformation from U into V, and then is the example, and then is what is the polynomials in linear transformation, and then invertible linear transformations and the inverse of T. First is important theorems on linear transformations. Number 1. Suppose U be a finite dimensional vector space over F, the field F, and suppose beta to be equal to the collection of the ordered bases for U, for this U, and suppose V be the vector space over the same field F. U is a vector space over the field F and V is also the vector space over the same field F. And beta 1, beta 2, beta 3 up to beta n be any vectors in V. These are just the vectors. Alpha 1, alpha 2, alpha 3 are the ordered bases for U. And beta 1, beta 2, beta 3 are the vectors, any vectors in the vector space V. And then there exists a unique linear transformation T from U into V such that T of alpha I is equal to beta I for I going from 1 to n. That is, T alpha 1 is equal to beta 1. Then T alpha 2 is equal to beta 2. So on T alpha n is equal to beta n. Right? Second theorem. Suppose U be an n-dimensional vector space over the field F, and let V be the m-dimensional. U is n-dimensional, V is m-dimensional vector space over F. Then the vector space LUV of all linear transformations from U into V is finite dimensional and is of the dimension product of m and n. Whatever of the dimension be the vector spaces, you just take the product of that. Third one is the vector space L from U to U of all linear operators. Please remember, when we write L from U to V, this is a linear transformation. And when we write L from U to U or V to V, when it is same, then we call this to be as a linear operator. This becomes the linear operator for the same vector spaces. So the vector space LUU of all the linear operators on an n-dimensional vector space U is of the dimension n square. Very important. Then fourth one is, let U, V and W be the vector space over field F. Let T be the linear transformation from U into V, and S is a linear transformation from V into W. T is a linear transformation from U into V. S is a linear transformation from V into W. Then the composite function, the product ST, the product of the linear transformation defined by ST alpha is equal to ST of alpha for all alpha belonging to U. So this is a linear transformation from U into W. ST is a linear transformation from U into W. Right? Please note that if T and S are linear operators on vector space VF, then both the products ST as well as TS exist, and each is a linear operator on V. But in general, these two are not equal. The values of these two are not equal. If these are linear operators, if S and T are linear operators, right? Okay, now let's move on to the example. T1 and T2 be the linear operator on R2, the second dimension, such that T1 x1 x2 is x2 x1, the interchange, and T2 x1 x2 is x1 0. These are the two definitions given to us. We need to prove that the product of T1 T2 is not equal to the product of T2 T1. So let's take this first. So the product T1 T2 on x1 x2, let's say. So this is equal to T1 T2 of x1 x2. And what is T2 of x1 x2 by definition? It is x1 0. Taking first value to be the same and second value to be 0. So this is x1 0. So this is x1 0. And now what is t1 x1 0 by definition? It is x2 x1, the interchange of these two. So this becomes 0 x1. Very fine. Okay. Now what is t2 t1 of x1 x2? Likewise we write t2 into t1 of x1 x2, and by definition t1 x1 x2 is the interchange, so this is x2 x1, and by definition of t2, so these two are not equal, right? So t1 t2 is not equal to t2 t1, so we have proved this. Next, about the polynomial. Let T be a linear transformation of vector space over the field F. Then the product of T and T is also a linear transformation on V. If T1 is T, T1 means you just have T over here. T2 means the square, that is we have to multiply T2 times. T3 will be the multiplication of T3 times. Likewise, right? Product of linear transformation is an associative operation. So therefore, if n is a positive integer, we define t the power n to be t multiply t multiply t multiply up to n times. Right? So definitely t the power n is a linear transformation of V. All these are linear transformations. So t the power n is also a linear transformation on V. Then t0 will be defined as I. Suppose n and l are non-negative integers, then t the power n into t the power l, this becomes t the power n plus l, the sum. And t the power n to the power l will be t the power n l, the product. Right? So the set LVV of all linear transformations on V is a vector space over the field F. When we have a linear transformation from V to the same vector space, we say this to be a linear operator. So T is a linear operator if T is a linear transformations from V into V itself, right? So the set LVV of all the linear transformation on V, that is, which means the linear operator is a vector space over the field F. It is a vector space over the field. The set is a vector space over the field F. Now suppose if I take all these scalars from F, the field F, then PT will be equal to the polynomial. This will be equal to A0 into the identity plus A1 into T plus A2 into T square up to so on an T the power n. This is also a linear transformation on V because it is a linear combination over F of elements of LVV. Right? So PT is called polynomial in linear transformation T. Next is the invertible linear transformation. Suppose U and V are the vector space over the field F. T is a linear transformation from U into V, such that T is 1, 1 and onto both. Then T is called invertible. So for invertible, two conditions are there. T should be 1, 1 and onto. Right? So now for the 1, 1, suppose T is a function from U into V, then T is said to be 1, 1 if I take the elements from U and alpha is not equal to alpha 2. If I take the distinct elements from this U vector space, then this implies what? T alpha 1 is not equal to T alpha 2. Or we can also say that if I take the two elements from the vector space U, and if these two are equal, then this implies alpha 1 is equal to alpha 2. Right? For onto, if T is onto, so for every beta belonging to this vector space V, there exists alpha belonging to the vector space U such that T of alpha is equal to beta. So T of alpha is equal to beta. This is the definition for onto. Next is inverse of t. If t is 1, 1 and onto, then we define t inverse from v into u. Let gamma be any vector in v. Gamma is any vector in v. As t is onto, so therefore gamma belongs to v implies there exists alpha belongs to u such that t alpha is equal to gamma. T is onto. T is given to be onto. So we have applied the definition for t. Now since t is 1, 1, so that alpha is a unique element of u. So for the two elements belonging to u which are not equal, we have t alpha not equal to t beta. So that we define t inverse gamma to be alpha. Now t inverse from v to u such that we have gamma belonging to this v vector space. So t inverse gamma is equal to alpha for every alpha belonging to u. If and only if t alpha is equal to gamma. T alpha is equal to gamma. Right? So t inverse is 1, 1 and onto. T inverse is 1, 1 and onto. Now are the important results on invertible linear transformations. Invertible linear transformations. Number 1, if t is a transformation from u into v, so it is a linear transformation, and if t is 1, 1 and onto, then t inverse will be the linear transformation from v into u. From v into u. Right? Second, now suppose a, b, c are the linear transformations on vf. We have three linear transformations, right? Then the product of a with b is equal to the product of c with a. So in both the sides we are having a to be common. Then these products is equal to the identity operator. Then this a, which is common, this a is said to be invertible and a inverse equal to b equal to c. Right? This is very important. Third, suppose t be an invertible linear transformation on vf, then t inverse t is equal to the identity operator equal to t inverse. And what is the uniqueness of inverse? Suppose a be an invertible linear transformation on vf, then a have unique inverse. Then fourth one, the necessary and sufficient condition for linear transformation A on VF to be invertible is that there exists a linear transformation B on VF, same, such that AB is equal to I equal to BA. I is the identity operator, so the product AB is equal to I equal to BA. Fifth one is very important. Let VF be a vector space and let A and B are the linear transformations on V. We have two linear transformations on VF. Then if A and B are invertible, then AB product is invertible and AB inverse will be B inverse into A inverse. If A is invertible and a non-zero element belonging to F, then the product of A and capital A is invertible and its inverse is equal to 1 divided by A multiplied with A inverse. Third one, if A is invertible, then A inverse is invertible and A inverse the inverse. Inverse of A inverse will be equal to A. So please remember all these points, results and theorems that are very, very important. So this is a quick revision for all the theorems, results, remarks for the linear transformations and invertible linear transformations. Thank you. Have a blessed day.